What is up, people, and welcome to another video on the Kubernetes Lightning series. If you're new to Kubernetes, check the link down below to the Kubernetes Lightning series playlist, where we take a look at Kubernetes from scratch. How to create your first container, we look at creating our first cluster, pods, deployments, services, and more. In this video, we'll be covering zero downtime deployments. So how to update a deployment, roll out new pods, and have traffic on those new pods without affecting any existing connections. We'll start with the very basic, obvious things to implement and move to more advanced things that you need to know. And we'll create a client that you can run to test this. So we got a bit to cover, so without further ado, let's go. So the first thing we need to do, and it's something I like to do in every video for those who are new, is to cover the source code. So if you take a look at the link below, you'll find a link to the Docker Development YouTube series GitHub repo, and everything we'll be doing in the series is under the Kubernetes folder. So if I look in this folder, you'll find deployments, you'll find pods, and everything related to Kubernetes. All the videos I do on this channel has source code and guide, readme files. It's all stored in here. Now in this video, we're going to need a Kubernetes cluster. And for a local Kubernetes cluster, I'd like to use a utility called Kind. It's lightweight. It allows you to run lightweight, small, fast Kubernetes clusters in Docker containers. It's much lighter than using a virtual machine. You can create multiple clusters and just throw them away when you're done. We're also going to need a deployment. And in this video, we'll have a deployment running 2 pods. And these 2 pods will be basically web API microservices. So to get a deployment and a cluster and everything up and running, what we're going to do is look at the source code, expand the Kubernetes folder, and look at deployments. And in here is a deployment.yaml file. This is the same YAML file we used in our tutorial regarding Kubernetes deployments. So in here I have a deployment with 2 replicas. It's called example deploy, and it's basically going to be running 2 pods. The container is just a Python microservice that we've taken a look at before. But for the beginning of this tutorial, the type or programming language or framework doesn't really matter, but it's going to matter later on. We use a container port 5000 to expose this service. It has some requests and limits and things like that. These things don't really matter for this guide, but we have a basic deployment with 2 pods. And to deploy this, we're going to use a utility called Kind. So at the top here, I've created some comments on getting a Kind cluster up and running. So we say Kind create cluster. We're going to call this cluster deployments, and we're going to run Kubernetes 1.31. I'm going to copy this line, and in my terminal, I'm going to go ahead and paste that, and that will go ahead and create a lightweight Kubernetes cluster that we can use for testing. And now that that is done, it only takes a couple of seconds. We can see our Kubernetes cluster has been created. We can do kubectl get nodes, and we can see we have a 1-node cluster running. And after a couple of seconds, we can see it's now ready. So now we have a Kubernetes cluster ready to go. And then I can very easily just apply this deployment YAML file by going to my terminal, saying kubectl apply -f. It's in the Kubernetes folder under deployments, and it's deployment.yaml. Go ahead and run that. That'll create our deployment. And if we do kubectl get pods, you can see we have 2 pods creating. And a couple of seconds later, if I do kubectl get pods, you can see they're now up and running, good to go. And then the next step would be to create a Kubernetes service to expose these pods so they can start taking traffic. You may also have an ingress in front of that to expose these pods publicly. That's the basic Kubernetes architecture for microservice and web applications. And the first thing you'll start to notice when there's constant traffic on these pods and you do kubectl delete pods, or let's say you do another kubectl apply when you're updating these image versions, you will notice small downtime in your application. This is because there are slight network interruptions that happen for a number of reasons. But let's talk about the basics of zero downtime deployment. Now, the first and most obvious thing for zero downtime deployments is that you need more than one pod running. That's the first and obvious thing. If you only have one pod running, that means your application is not highly available. Now, although you may be able to update Kubernetes and tell it to create a new pod, send traffic to that new pod and drain the old one, and then still remain with one pod running, I would always suggest in a highly available production environment to run at least minimum 2 pods. This is because the cloud is flaky. A virtual machine instance can be terminated at any time. Also, if the actual pod itself becomes unstable, depending on the web server you're running, you only have one pod and nothing to recover from there. And this is where health probes and those sort of things come in. But I would recommend to always start with 2 pods. So to do that, it's very simple. We go to our YAML file, and under the deployments, we just want to make sure replicas has a value of 2 or higher. This will just naturally make our application more available and resilient. Now, on my channel, I have covered things like liveliness, readiness, and startup probes. Now, this is a little bit of a side topic, not really related to zero downtime deployments, but for highly available services, you'll want to go ahead and configure a liveliness and a readiness probe. This will make sure if there's any instabilities in one of the replicas, Kubernetes may remove traffic from that replica, but it also may restart the replica depending on the probe. But that's more for highly available deployments. In this video, we'll take a look at zero downtime. So I'll start with 2 replicas. The next setting, which is a little bit of a more advanced step up from just setting the replicas, is the deployment strategy. Deployment strategy allows us to tell Kubernetes how we want pods to roll out. Now, this is not only important for zero downtime deployments, but it can also make your deployments a little bit more efficient. If you have really slow starting pods, you may want to update a deployment strategy to create more pods when Kubernetes has to roll new ones. So if you're running 10 replicas, it might be very slow to create one replica at a time and wait for it to become ready, especially when you're using slow startup probes and your application is quite slow when starting up. So this is where you can start playing around with deployment strategies to make your deployments a little bit faster and smoother. But for zero downtime deployment, it's also important to understand how rolling deployment works. You can tell Kubernetes exactly how many pods to roll and how many pods it can take down in terms of the old pods. So Kubernetes will create new pods and take down old pods, and there are settings where you can adjust how many new pods to create at a time and how many pods are allowed to be removed at a time. So if we take a look at our deployment YAML, we have our kind deployment. If we take a look down at the spec, under the spec you have a field called strategy, and you have different types of strategies. You've got rolling update, and this means Kubernetes will just roll new pods, create new pods and take old pods down. So new pods will create and old pods will terminate. But here specifically we're telling Kubernetes to have a max surge of 1 and max unavailable of 0. So there are different strategies for Kubernetes deployment that you can learn about. If you set the strategy type to recreate, it'll basically kill all the existing pods before new ones are created. Now, this might not be suitable for us in our microservice world where we always want services up and running. Other types of strategies can be rolling update. Rolling update is the default value. The deployment updates pods in a rolling update fashion, basically creating a new pod, taking an old pod down, then creating a new pod, taking an old pod down, etc. And you can tell it how fast you want new pods created and how slow you want old pods taken down. This is with the 2 fields, max unavailable and max surge. Max unavailable is quite obvious. This is an optional field that specifies the maximum number of pods that can be unavailable during the update process. So for example, in my YAML file, I've set the max unavailable to 0 because I only have 2 replicas. It can take one down and make sure that none are unavailable. This is also important for services where you have maybe some high traffic load. Let's say you have high traffic load and you always want 10 pods available. You don't want the deployments to reduce it to 9 ever. You may want it to always create new ones and maintain that number of 10. And max surge is an optional field that specifies the number of pods that can be created over the desired number of pods. So you can basically tell Kubernetes to create a lot more pods, especially if you have slow starting pods. It allows you to roll your updates a bit quicker. So that's as simple as that. The rolling update settings just allow you to control how pods are rolled out. out how many new pods are created and how many old pods are terminated, and the number of pods that will always be available during the rolling deployment. This will make sure your application is highly available and you won't have bursts of traffic coming to a new pod during deployment, or sudden bursts of traffic going to old pods during deployment. So now that we have enough replicas available, we have set replicas to 2, and we also know that we're going to have enough replicas during deployment because we've configured our rolling deployment correctly. The next thing we need to understand is a little bit about the networking, the IP addresses, service discovery, and load balancing, how these 2 pods that we have are load balanced during a rolling deployment. What happens to the traffic? In a previous video, we've taken a look at service discovery and load balancing using a thing called Kubernetes service. So if we take a look at our cluster and we say kubectl get pods O wide, we get the IP addresses of those pods. We've learned that we can run curl commands to these IP addresses, so we can access these services using the IPs. The problem is when a rolling deployment happens, we'll get new IP addresses. So that is not going to work. IP addresses also change. They're not really good for server-to-server communication. That is why in these microservice and web world, we use DNS. And to get a fixed DNS for our 2 pods over here, we need a Kubernetes service. So in our Docker development YouTube series under Kubernetes, we have a services folder on the left here with a service.yaml. So this is the service.yaml that we've taken a look at in a previous video. And if we deploy this Kubernetes service, we'll get a DNS name called example service, and it will expose a port, which is port 80, and it'll map port 80 to port 5000. Check out that Kubernetes services video for more information. What I'm going to do is I'm going to deploy that service. So I'm going to say kubectl apply -f in the Kubernetes folder under services. I have services.yaml. Go ahead and apply that. Then I can say kubectl get service, and we can see we have our example service over here, and it's exposed via this IP address. So all the traffic that comes to example service will go to our deployment, and we can see that by saying kubectl describe service, and we'll get our 2 endpoints. These are our 2 pod IPs and port 5000. If you do kubectl get pods O wide, you can see those are the pod IPs that are matching. So our endpoint is correctly sitting behind this Kubernetes service. This is important to understand because when we do rolling deployments, we want a service discovery mechanism. We're going to have new pods come up with new IP addresses, and they're going to be joining this Kubernetes service. So new traffic will start flowing to the new pods. And then when old pods are terminated, the old IPs will be removed from this service. And behind the scenes, Kubernetes uses technologies such as IPVS or IP tables to manage these networking rules. So IP tables will be updated on our Kubernetes nodes to remove the old IP addresses and add the new IP addresses during a rolling deployment. Kubernetes manages all of that stuff gracefully. So Kubernetes will not add a new IP for a new pod to this Kubernetes service if the pod is not yet even running. Otherwise, that would obviously create an outage. So Kubernetes manages all of this stuff for us. We don't have to think about it. But it's good to understand this, as Kubernetes services play an important role in discovering these new rolling deployed pods. So now that we have 2 pods that can rolling deploy, and we also have a service with a fixed DNS endpoint sitting in front of our 2 pods are now able to receive traffic. And this traffic could be coming from an ingress controller, it could be coming from a load balancer, depending on the service type. That all doesn't really matter. Just pretend our 2 pods are constantly receiving traffic. Now I'm going to show you that by default, generally microservices don't have zero downtime deployment. Even though Kubernetes does all this graceful rolling of pods, there are a couple of important things to understand. In order to do so, what we're going to do is create a small pod in our cluster where we can run a small shell script that runs in a loop and generates traffic. This will constantly send traffic to our deployment, and we can monitor for errors. And when we have this, we can do a rolling deployment, and I can show you that our deployment is not graceful. So what I'm going to do is just deploy a small client using kubectl kubectl. So let's go to our terminal. I'm going to create a new namespace. I'm going to say kubectl create ns, create a namespace called client. Then what I'm going to do is I'm going to just using kubectl create a small Ubuntu container that just sits and sleeps. So that'll provide me with a container I can run a command on, and I can start sending traffic from there. So to do that, what I'm going to do is I'm going to run this command kubectl in the client namespace. I'm going to say run a container called client, and my image is just going to be Ubuntu. I just need a Linux OS, and my command is going to be bash, and I'm just going to say inside my bash command, I'm going to say while true do sleep for 3600 seconds and done. If I run this will just create a pod, one pod that I can use for testing. I can do kubectl -n client get pods. We can see our pod is creating and give it a few seconds. Now it's running, and with that now running, I can do kubectl exec -it exec into the client with bash. So now I am in this client pod. I can use it to generate traffic to our deployment. Just basically use this to test zero downtime, graceful deployments. So what I can do now that I'm in this client is I can say curl and curl that URL. So this is the example service we've just created before that's living in the default namespace that's exposing port 80. Now I don't have curl, so I can say apt-get update and apt-get install -y curl. This will just go ahead and quickly install curl in this container. And then I can say curl, and look at that, we've got hello world. So now we're able to send traffic to our service. So what we can do now is we can wrap that in a while loop. So just go ahead and do this. While true, do, and then say curl, and then sleep for 0.5 seconds, echo just to get a new line, and do done. So this will run in a loop, and look what happens. Every time this runs, we should see it sort of flashing and getting a response and moving to the new line. So now we have constant traffic on our two pods, and if I go and run kubectl delete pods -all, it'll delete those pods, and we shouldn't see any downtime over here. If we go back, we can see it's being deleted. Kubectl is holding this command here. If I press Ctrl C and I do kubectl get pods, we can see the new pods are running. They're 20 seconds. As soon as they get to 30 seconds, these old pods should disappear. So these old pods will sit in terminating status till 30 seconds has passed. You can see it should have passed. So if I do kubectl get pods now, you can see the old terminating pods are now gone. This is because by default, Kubernetes has a grace period of 30 seconds. This grace period is called termination grace period. When we delete pods, we saw that the pods go into a terminating status. What happens then, as soon as a pod goes from a running into a terminating status, Kubernetes sends a hang-up signal to our pods that it wants to terminate. It then starts a timer that will run up until the default, which is 30 seconds. If the pod does not shut down within that 30 seconds, Kubernetes will then again send a kill signal to forcefully terminate that pod. That is why we can see our pods stay in a terminating status for a longer time. And when we delete pods, we expect the curl command in the loop here to run and not show any connection errors. We don't want to see any downtime. If you see any hold up here, timeouts or connection errors coming back from curl or non-200 responses, then you know you don't have zero downtime deployments. So now we have our two pods. We have graceful rolling deployment. We have a Kubernetes server sitting in the front. We've got constant traffic going to both pods. And we have this client pod that we can use to test zero downtime deployments. Now it's important to understand exactly what is happening when we delete these pods or when we do a rolling deployment. As I mentioned before, the pods that will be taken down by Kubernetes will go into a terminating state. And Kubernetes will start creating new containers based on our deployment strategy. So we'll have two new containers be created, and the old two containers will go into a terminating state. Kubernetes will send a hang-up signal there and start the timer for the termination grace period. It'll basically give each of the old pods 30 seconds to shut down. Now, during all this time, what Kubernetes does is it creates new IP addresses for the new pods, new routing rules in terms of IP tables. We learned about Kubernetes services in the previous video. Basically, it sets up that that new Kubernetes service so that new traffic and new connections from our client starts to go to the new containers as soon as they're ready and up and running. So the new pods come up and the traffic starts to hit those two new pods. Kubernetes will automatically stop sending traffic to the old pods. And this is already happening right now. And as I mentioned before, if you see any interruption happening from your client, that curl that's running in a loop, you know your deployment is not graceful. Now the outcome here is highly dependent on the type of service you're running, whether it's a .NET, a Python, Golang, Node.js, Nginx, whatever kind of web server that's running, because all of these frameworks and servers behave differently when it comes to shutdown signals. There are two things that you need to understand as a DevOps engineer when looking at Kubernetes zero downtime deployments. Two major factors is one is application startup. You want graceful startup. You also want graceful shutdown. We've taken a look at now that Kubernetes has a termination grace period seconds, which is configured by default to be 30. The first thing I would do, and it's highly recommended, is to go and set this explicitly in your YAML. I don't like to rely on default values, but in order to set this, you also have to understand what is the longest running requests for your service. This hello world is not really a good example because it immediately responds. In the real world, requests might take a couple of seconds, especially when you have microservices that rely on storage and databases and external systems. You might have API calls that take 10, 20, 30, 40 seconds or even longer sometimes. If they run longer than the termination grace period default of 30 seconds, you will have an interruption during your deployment. So firstly, let's go ahead and set termination grace period. We'll also want to understand how our application behaves when it comes to shutting down. In this example here, I'm using Python and I'm using a Flask web server. And in the basic Flask setup, it does not honor shutdown. But because my requests are really quick, it doesn't really matter. We don't get downtime during our deployment because Kubernetes automatically starts routing the new requests to the new pods when they're ready. It stops routing to the old pods, and existing connections that are going to the old pods are so quick. They're quick enough that the old pods drain really quickly. So there's no downtime. Let's go ahead and make our microservice a little bit more realistic by making it take a little longer to come back, and I'll show you what termination grace period does. So Kubernetes gives us the option to add termination grace period and control it. And I would always recommend that. So if you take a look at your deployment.yaml under spec, you'll want to go ahead and configure termination grace period seconds and set this to a number that you know is long enough to wait for any connections to finish. So if you know your service takes roughly 10 seconds to respond to requests, maybe set this to something like 20 or 30 seconds. I would always recommend to explicitly set this value and not rely on the defaults, even though the default is 30. So what I'm going to go ahead and do is just set this value, go to my terminal, and I'm going to say kubectl apply -f, and that'll configure our deployment. So now we have our termination grace period seconds set. Kubernetes will send a hang-up signal to pods it wishes to terminate, and it'll wait for 30 seconds. Now if we go back to our GitHub repo and we scroll down, there is a Python folder, and in there is a source folder with a server.py. This is the basic Python microservice that we're using for this demo. Now if I go ahead and say import time and I add some artificial sleep here like time.sleep, set it to 10 seconds, we can basically simulate an application that takes a little bit longer to respond. So in our case, this will take 10 seconds to respond. And because it's under the termination grace period of 30, it should still be good to go. The other thing I'm quickly going to do is set an image pool policy. So instead of saying image pool policy always, I'm going to say if not present, because I'm not going to be pushing my images to a registry. I'm just going to use kind to load them so it's quicker. Then I'm quickly going to change directory to the Python folder, and I'm going to do docker build, and I'm going to tag this image as Python test v1. Just rebuild that quickly, and now that that's built, I'm going to push that image to kind. I'm going to say kind load docker image Python test v1, load it into my cluster called deployments. Go ahead and run that. That'll load it into kind. Then I can jump back to my YAML and say I just want to run that image. Go ahead and save that, and then quickly apply that by saying kubectl apply and apply the deployment YAML. Kubernetes will roll the new pods. You can see it created 2 new pods, and once they're up and running, it sends termination to the old pods. And if I go back to my client now and I run this curl in a loop, we'll see that it'll take a little bit longer to get a response. It's hanging here now. That is because it's going to take 10 seconds for each request to complete. So you can see there's the first request, 10 seconds later you'll get another one. So you can kind of simulate longer running requests. It's also a good test to perform. Then I can say kubectl delete pods and go back here, and we shouldn't see any interruption. This is because this open connection, well, the new connection that we see here now is going to the new pod, but any open connection during this curl loop will have enough time to finish because of the termination grace period within Kubernetes. Kubernetes will wait 30 seconds, and we know our request takes 10 seconds. So there's no race condition in this case. We're allowing enough time for our application to shut down and finish old connections, and new connections will go to the new pods. If we jump back to our Python application and we extended this to 40 seconds, for example, and we build this one as v2, and then we load v2 into kind, and we jump to our deployment YAML, update that to v2, and jump back to our terminal and kubectl apply that. Once these 2 pods are now rolled out, we can do the same tests and you'll see impact. So now we got the new pods up and running. Can head over to my other terminal and just run that curl command in a loop. If I delete all the pods, you'll basically see that this existing connection here will be interrupted. This termination grace period is set to 30, so Kubernetes will only take 30 seconds. It's going to wait 30 seconds to terminate these pods and then forcefully terminating them. And what will happen is this connection, we can see we have an empty reply, has been interrupted. So this is a prime example of the Kubernetes termination grace period set too low when our requests needs more time to respond. And then we can see new requests have started working, but old requests were interrupted. So the fix here is easy. As we know our requests take long, we need to just adjust the termination grace period seconds. So Kubernetes allows us to wait for applications to shut down, but we've also learned that every application can be different. You have to be aware of how long network requests take. So you have to understand the network requests of your application. Are they very quick or are they long-running requests? The other thing to consider is you have to understand the framework that you're using or the web server that you're using to host your application. In my case, it's Python Flask, and as we've seen, Flask doesn't really handle shutdown. If we switch to something like a .NET Core microservice, it runs on a different runtime, a different framework. It has a different web server under the hood, and that web server may be written and configured to handle graceful shutdown. So when the Kubernetes hang-up signal went to our pod, it lasted for 30 seconds. This is because Flask does not respond to those hang-up signals, and it will take a developer to write more code in that service to listen for that signal and gracefully shut down. So we saw that our shutdown would always take 30 seconds. If we extend our termination grace period, the Python program will just wait for 50 seconds if we extended it to 50. With other frameworks like the .NET Core framework, .NET Core will actually wait for all connections to finish and then shut down itself. So it may shut down earlier than your termination grace period, but there is a caveat. .NET Core by default is something like 5 or 10 seconds to shut down. So if you have long-running network requests, like in our case we have a 40-second delay, a .NET Core microservice will be impacted. So to show you this, I have switched to a different application. So in our GitHub repo, I've got a C# folder as well, and in there is a program.cs. So this is a minimal API for C#, and it's the same as the Python one. We have an endpoint here where we sleep for 40 seconds and then we return hello world. For this one, I also have a Docker file running .NET Core 8. So what I'm going to do, in my terminal, I'm just going to say cd ... and then cd into the C# folder, and let's build that and tag it as .NET Test v1. Go ahead and run that build. Now that that's built, let's load that Docker image into our kind cluster by using the kind load command. Then we're going to jump back to our deployment, and we know that our service takes 40 seconds. So let's go ahead and bump our termination grace period up to 50. So we know that our deployment should be technically be graceful now. So let's go to the image, change this image over to .NET Test v1, go ahead and save that, jump back to our terminal and say kubectl apply. So you'll notice two new pods create. These are now .NET pods and the old Python pods are terminating. And now I'll demonstrate to you the difference between two different web servers and that they have different behaviors. You need to understand those behaviors in order to understand graceful shutdown. In our Flask application, Flask did not handle graceful shutdown. It was just running until Kubernetes killed it after the termination grace period. And it just happened to be that our microservice was pretty quick at responding, so that traffic will go to the new one, all traffic will drain from the old pods, and we won't have any interruption. But if you have longer running requests, we learned that we need to change the termination grace period. But now when we look at this, we've got .NET pods running, but if I go to our client and I run this curl in a loop, you can see we've made a request, and if I go and say delete pods all, now the hang-up signal is sent to our .NET apps, but notice what happens. If we take a look at this output, we can see the connection was reset by peer. We got an error, so we got an interruption to our deployment. Now why is that? This is because by default in ASP.NET Core, the web server has its own termination shutdown period. And if we take a look at the Microsoft documentation, there is a shutdown timeout. Specify the amount of time to wait for the web host to shut down, and the default is 5 seconds. So when Kubernetes sends that first hang-up signal notifying the pod that it should shut down, the web server will only wait for 5 seconds for connections to finish. And because our request takes 40 seconds, ASP.NET will shut down within 5, killing that connection. Now we can fix that by setting this ASP.NET Core shutdown timeout seconds value. This is an environment variable we can set on our pod spec. So if we go to our YAML and we say environment, and we can go ahead and set this value as an environment variable, and we can set it to match our termination grace period of Kubernetes. That'll tell our web server to wait for 50 seconds because we know our request takes 40. This will allow enough time for our web server to shut down and finish existing connections. So now what I can do is I can say apply that, and now we have that new change rolled out. I can go run my traffic and I can say kubectl delete pods all, and now we can see we should not see any impact to our traffic. That connection is still open. ASP.NET is allowing for it to finish, and after a couple of seconds we can see that request has finished. And if we do kubectl get pods, our new pods have rolled out. So our deployment is now graceful. So now we've learned how to handle graceful shutdown, both from the Kubernetes side as well as the application side. Now this is mostly for web services. If you have an application that's listening to a queue, like a RabbitMQ, a Kafka service, or some kind of streaming service, message broker, which does not have to drain incoming connections, you would have to write logic to handle graceful shutdown. Generally, programming languages allows developers to listen for exit signals. These signals are called SIGTERM and SIGKILL. They're basically hang-up signals that the operating system will send to processors. Developers would write code to listen for these signals and then finish doing what they're doing. If you're listening to a message queue and you get that signal, finish processing whatever it is you're doing and you'll shut down gracefully. So this is up to development teams to implement. But this all demonstrates graceful shutdown. But what about graceful startup? So in our case now, our applications are shutting down gracefully. But what about the new applications that create? These new applications might not be ready to take traffic. For very lightweight microservices, they generally start up in milliseconds and they're up and running to take traffic. But there's always that race condition. There's always that chance for that service not to be ready. If you have slow starting microservices, you might have a race condition where the actual service is not really ready to take traffic. This is where startup probes and readiness probes come in. I've got videos on those on the channel. If you go on the channel and search for probes, you'll find them. But let me show you an example of our Python microservice that's not ready to take traffic, and how do we solve that without writing code. So what I'm going to do is I'm just going to jump back for a second into my Python Flask application, and I'm just going to write some code which pretends I'm not ready to accept new new connections. So what I'm going to do whenever I get a request, and first what I'm going to do is I'm going to calculate the current time less than the start time, and I'm going to calculate whether that is less than 10 seconds. So here we're simulating that our application takes 10 seconds to warm up. So if we get a web request within 10 seconds of our application startup time, we'll return a 503 saying application not ready yet. So think of this as an application that warms up. It starts up slow. Maybe it's a slow web server. Maybe it has to go to the database to read some data. Maybe it has to read files before it's ready to take traffic. That means when Kubernetes starts this pod, the IP tables are set up by the Kubernetes service. The traffic will immediately start coming to the service, but the service is not ready. This happens often in real microservices. So that's what we're simulating here. And I'm also going to remove the sleep because we no longer need it. Going to go ahead and save this, jump to our terminal, go back to the Python folder, and let's go ahead and build Python test v2. And now that that's built, I'm going to say kind load that image. I'm going to jump back to our deployment, and I'm going to go ahead and set our image to Python test v2. Go ahead and save that, and then I'm going to say kubectl apply to apply that change. Get pods. We can see our new pods are up and running. But look at what happened to our curl commands. You can see we got these 500 errors, and then it started working. I can simulate that again by going here and delete all the pods, jump back to curl, and you can see our new pods are not ready to accept traffic. As soon as that 10-second has passed, it'll automatically recover. So this simulates pods that are not ready to take traffic. Now, how do we solve this? To solve this, Kubernetes has a concept of readiness probes and startup probes. If you have a slow starting microservice that's very, very slow, especially like legacy apps, I would highly recommend to take a look at startup probes. If you're just trying to solve for a small race condition where a service might not be ready, I would highly recommend a readiness probe instead. The cool thing about readiness probes as well is that if your web server has a small glitch or a hang-up, or your web server is hanging, Kubernetes will detect it and it will automatically remove the traffic from those pods, preventing customer impact. So readiness probes are really good for high availability. So to solve this problem, what I'm going to do is jump back into our YAML, and I'm going to go ahead and add a readiness probe over here. So here we say readiness probe, which is going to be an HTTP GET, and you can put an endpoint in here with a port. So Kubernetes will ping this endpoint, and it'll ping it every 3 seconds with an initial delay of 8 seconds. So we can configure and say how long you should wait after the pod has started up. So if we know our pod starts up in 8 seconds, we can go and set it to 8 or 10 seconds, or if we don't know, we can set it to a rough estimate time. Kubernetes will not send traffic until this readiness probe starts to respond. So I go ahead and save this. Let's go ahead and apply that. And now we should see that the pods take a little bit longer to become ready. You see the status here, ready, 0 out of 1, and its age is 8 seconds. Once it says 1 out of 1, that means it's fully ready and accepting traffic. So now we can see our new pods are up and running. They're both ready to accept traffic, and the old pods got the hang-up signals and they're shutting down. So what I can do now is go into my terminal, go back to the client, start generating that traffic. Our pods are now up and running. Go ahead and delete all, and we shouldn't see any impact. This is because the old pods are getting the traffic until the new pods are ready. Once the new pods are ready, they'll start taking the traffic, and the old pods will get their hang-up signals and exit gracefully. So this covers graceful startup. There's another utility I'd like to show you that you can use to generate more realistic traffic to your service rather than a bash loop. When you write a bash script that loops and makes a connection using curl, especially when you're doing these types of simulations, you have to understand network requests and that there can be race conditions to certain things and certain scenarios. For example, if you have a sleep, you can only have one connection at a time, and this might create issues when you're trying to test a realistic scenario. So to solve this, I'd like to use a utility called WRK, which allows me to specify how many customers I want to create, what endpoint I want to hit, for how long, and what time timeout. It's a very useful utility because rather than making one connection at a time in a loop, the utility like WRK will start multiple threads and create connections. This means you can have concurrent traffic hitting your endpoint, which is a little bit more realistic, and it'll print the results like the response time, the requests per second, and the number of errors. So if you can see any errors, you know there was an impact to your deployment. If you want to try out this utility, it's very easy to use. To install it, you can say apt-get install -y wrk, and then to run it, it's a very simple command. You say wrk, you tell it how many threads you want to create. So this is like 10 customers basically, and then you provide the number of connections you want, and I always recommend to keep the connections the same as the number of threads that you create. This means you'll roughly have now 10 customers creating requests, or 10 clients. We want to run our tests for 120 seconds, so this is the duration -d, and it's important to set a timeout. So this is the timeout that WRK will wait for a response before closing the connection, and then you specify the endpoint. So I can say I want to run a test for 20 seconds, make my timeout 5 seconds, go ahead and run that. That'll create 10 connections. I always recommend to run a before and an after, so you understand the output before, so you know what the baseline is. If you take a look at this, you can see we got pretty good results. So this is our latency, requests per second, how many requests it sent, and you don't see any errors over here. So that means there was no impact to our deployment. So when I delete the pods, I'm expecting similar output. So what I'll do is jump to the terminal, get ready to run this again. But what I'll do is I'll also get ready to delete the pods. So I'll start this and then delete the pods, and we shouldn't see any interruption. And there you can see we don't have any interruption to our deployment. So WRK can be a really handy tool to do something similar, just a little bit of a more realistic scenario. So that's it for that is how you achieve zero downtime deployments. You have to have a good way to test it. You have to understand the application side, how shutdown is handled, how Kubernetes handles termination grace period, how application may not be ready to accept new connections, and how Kubernetes can help us solve for readiness and warm up in slow starting applications. So our application terminates gracefully and it's able to handle connections in a graceful manner. So hopefully this video helped. If you liked the video, be sure to like and subscribe, hit the bell, and check out the link down below to the development of the Ultimate DevOps course. And if you want to support the channel even further, hit the join button down below to become a YouTube member. And as always, thanks for watching, and until next time, peace.